All right, let's do this. So this week we're going to be talking specifically about two phases of matter out of the three that we're going to study in this course, solids and liquids. All right, we were kind of first introduced to these states of matters when we were doing our balanced chemical equation. We know that each element has a standard state that's either a solid, a liquid, or a gas. All right, now we're kind of going to formally introduce these here. What we have pictured below in our first cup is a solid. My handwriting's, come on. In our next cup is a liquid, and in our next cup we got a gas here. All right, so let's talk about these properties of our different phases of matter, and we're going to start by discussing on a micro scale perspective. Right? By micro scale, I mean if I shrink down in my magic school bus and I'm looking at these individual atoms or molecules, what would I be looking at? Like, how do these different phases of matter compare? All right, so first of all, with regard to their neighbors, and specifically neighbor proximity. Right? Solids, those two molecules are butted right up against one another, very, very close to one another. So our neighbor proximity is very close for solids, and it is also very close for liquids. In liquids, those atoms or molecules are also right up against each other. All right, but this is what makes these very distinct from the gas phase. In the gas phase, atoms or molecules are very, very far apart from one another. So much so that we consider them not to be interacting at all. Right? So as solids and liquids are very close. All right, our gas molecules, our neighboring molecules, are very far apart from one another. All right. Also, if we think about the position of our atoms or molecules in a solid, those positions are fixed, right? Your neighbor is your neighbor, and it's going to be your neighbor tomorrow and your neighbor in 100 years. Importantly, molecules and atoms, they're always moving around, but in a solid, they're kind of just like vibrating in place, right? But again, you're not sort of moving, your position is fixed. And this is different from liquids. Although liquid molecules are very close, they're interacting with one another, they're always changing their position. They're kind of tumbling around in space. And then in the gas phase, these things are just ping-ponging around inside these containers. These also have a variable position here. All right, so if we shrunk down, what we would see is a solid is composed of atoms or molecules that are really close together and they're kind of stuck in place. They're staying put. Liquids, they're also really close together, but they're kind of tumbling around one another in space. So whoever you're interacting with right now, it's going to be different a few seconds from now. And then in the gas phase, these molecules are very far apart and just moving around, kind of ping-ponging around inside that container. All right, so again, that would be like a micro scale perspective. If we shrunk down, what would we see looking at these different phases of matter? All right, so now we're going to talk about what we would call a macro scale perspective. And that is if we were to see it with our eyeballs at the scale in which we are, which is very, very much bigger than atoms or molecules. All right, so what do we see that differentiates these three states of matter? All right, so first of all, we are going to talk about the shape of this substance. Our example solid here is a cube. If we took it out of that cup, it would still be a cube. If we put it into another cup, it would be a cube, right? So the shape of that solid is fixed. All right, but the shape of our liquid is going to depend on whatever container it's in. If I take this and put it into a smaller cup, it's going to look different than if I poured it on the floor, right? So our shape of our liquid is variable. It's going to change depending on what vessel it's in. All right, and then our gases, their shape is also variable, but in kind of a very special way. Gases will always completely fill whatever vessel they're in. That means if we put it in a bigger vessel, these gas molecules would expand. They'd get even further apart to fill that vessel. If we took this container and we compressed it into a smaller volume, our gas molecules would become closer together. Okay, and so that leads us to the next one. Just like our shape for our solid, its volume is also fixed. All right, if we measured that length, width, height business, we could calculate the volume, and since that shape isn't changing, the volume isn't changing either. Again, this is what makes solids different from the behavior of liquids, because liquids, while they have this variable shape, they'll take the shape of whatever container they're in, their volume is also fixed. That's why when you go and you measure out 1 cup from the sink and then you go and you pour it into your recipe, it doesn't stop being 1 cup, right? That volume's the same no matter what container that liquid is in. And then a gas, again, it's going to completely fill whatever vessel it's in. It will expand or contract, so it has a variable volume. Cool. All right. Let's talk a little bit more about these different phases of matter. Most substances can exist in all 3, and it depends on temperature, right? So if we just think about water, water can be a solid at what? High temperatures or low temperatures? Low temperatures. And then gas at what? High temperatures or low temperatures? High, right? So we can sort of take its substance and transition it through these different states of matter. And we have fancy words for that. All right, if we're going to turn a solid into a liquid, this is a process we call melting. Okay, and the temperature at which this happens, we call the melting point. And if we take a liquid and turn it into a solid, what do we call that? Freezing. And these are just inverse of one another. We can turn a liquid into a gas. All right. If we do this based on increasing the temperature, let's think about a pot of water. We crank up the temperature, and what starts happening to our liquid? It starts boiling. All right. Evaporation is a little bit more complicated of a process that we'll talk about next class, but that happens at room temperature, right? The boiling is one that you drive by increasing the temperature. And then a liquid can turn back into a gas, process called condensation. All right. These are all these temperature-dependent, what we call phase changes. There's also another one which is pretty rare. Not all substances will undergo this transition from the solid to the gas phase without ever passing through a liquid. This is a process called sublimation. All right. Fun fact, again, certain substances do. It turns out to be very useful in organic chemistry because a lot of organic solids will sublimate, and you can use it to purify those solids. All right, cool. So we're going to talk about these solids and liquids this particular chapter, and then we're going to kick gases off. They're kind of a bigger topic that we'll discuss on their own here, right? So we're going to take these states of matter one by one here. Today we're going to focus on solids, and we're going to discuss the different types of solids that exist. So first we have ionic solids. Remember, ionic compounds consist of what on our periodic table? What two type of elements? Metals and nonmetals. All right, and we looked at the structure of these ionic compounds a few times, and I tried to draw them, and here the textbook did a much better job than me, right? So we can see this 3D shape here. This is sodium chloride. In purple, we have our sodium ions. In green, we have our chloride ions, and we can see it's just this repeating array of green and purple, right? Positive charge, negative charge, and it goes in all directions. It goes in this direction, goes in this direction, and it goes in that direction. Right? And this is just a small snapshot. Imagine that just continuing forever and ever and ever, because these things are so small that even in a teeny tiny crystal of salt, you have a whole bunch of ions going on in there, right? Again, just this big repeating network, what we would call a repeating array of positive and negative charges. Oh my gosh. All right, and let's think, what is it that's holding that solid substance together here? Is that opposites attract interaction between those positive and negative charges, right? Opposite charges want to be attracted to other opposite charges, okay? So our ionic bonding, and we got a fancy term for this here. Ionic bonding is what we call electrostatic forces. All right, and that word electrostatic, that's our opposites attract. Fancy word for saying opposite charges are attracted to one another. All right, in the grand scheme of things, these electrostatic forces are very strong. We're going to talk about a lot of ways in which molecules and atoms interact with one another. The electrostatic forces are very, very strong interactions between these neighboring ions. All right. So, next thing we're going to talk about these solids is what we call the melting point, transitioning from being a solid to a liquid. And importantly, if I'm going to melt this solid, that means that all of a sudden everybody that used to be neighbor to one another and fixed in place, now they're tumbling around in space here. So you got to break some of those strong electrostatic forces, and that's why our melting points are quite high compared to most solids. Again, a consequence of those very strong electrostatic forces. Okay? So we're saying these things, they're held together by these really strong forces. And so you would think, well, that must make these solids themselves really strong pieces of material. But if you think about it, we don't build buildings out of salt, right? So what's the deal here? Let's think about it. Let's say that I were to take a hammer and I'm going to smack the crap out of this side of this solid right here, right? And I hit it really hard, and now all of a sudden everything gets shifted down right here. Right? Does this look like a nice, happy, stable solid? No, now I have these like charges repel going on here. I have these groups of positive charges next to each other and negative charges. And so what I would have just created is a little fault line where this thing is just going to crack in half. All right? So although these are very strong interactions, they have very high melting points. We consider these to be brittle solids, which is a fancy way of saying that they will break or crack under pressure. so our ionic solids made up of metals and nonmetals, this repeating array of positive and negative charges. The forces holding that solid together are these very strong electrostatic forces, which give these compounds high melting point, but because of their structure, under pressure they would crack and are considered to be very brittle. Cool. All right, so ionic compounds we talked a lot about before. We also talked a lot about molecular compounds or covalent compounds. Whereas our ionic solids are metals and nonmetals, our molecular solids are only which one? Only nonmetals. All right. Yeah, please. The structure of these molecular solids, importantly, your little building blocks for your molecular solids are these molecules, right? So these are made up of molecules. And remember, our molecules are covalently bound cluster of atoms. All right, that's what a molecule is. Think of a molecule of H2O. It's hydrogen and oxygen, and those hydrogens are covalently bound to those oxygens, right? So these are these little building blocks that make up our molecular solid, all right? Importantly, when we're talking about a molecular solid, like ice, the two neighboring water molecules are not covalently bound to one another. They are themselves a cluster of covalently bound atoms. They have hydrogens and oxygens that are covalently bonded. But the two water molecules next to each other in that solid chunk of ice do not have a covalent bond between them. Okay? So we need to make this is really kind of important because we got two different types of interactions going on within these solids. We have these molecules that are covalently bound clusters of atoms, but importantly, we're going to note that neighboring molecules are not covalently bound to one another, let's say. All right. Instead, we have this new category of force that we're going to talk about. Intermolecular forces. They are what hold neighboring molecules together. All right, we got this new term here, intermolecular forces. I'm going to kind of leave it at that, other than to say, let's pick this word apart real quick. Intermolecular simply means between molecules. So these are the forces between molecules, all right? And these are what are holding our solid together. So let's just kind of zoom in here and see if we can't understand what I mean. We're going to look at the structure of ice, all right? And what we see here is just a single water molecule. We have these hydrogen atoms here in white and these oxygen atoms here in red. And we can see this stick. These are these molecules, these atoms covalently bonded together. All right? So now we're going to look at a neighboring water molecule. And we see it's got its oxygen here. And it's got its hydrogen, and the other one's kind of tucked back here. But again, these two molecules are not covalently bonded together. They have this different type of interaction that's holding them together, what we're going to call intermolecular interactions. And we will do a little bit of a deep dive about the different types of intermolecular interactions. But right now, you're just going to trust me, right? But the bottom line is, if we looked at this structure here, hopefully it doesn't get too ugly. we see that now there's a neighboring water molecule. And again, it's got its hydrogens and its oxygen. And they're covalently bound together with these little sticks. But they are held together or interacting with this neighboring water molecule through a different type of intermolecular interaction. All right, so if we look at ice, if we zoom in, what we would see is this repeating network of water molecules. Each water molecule is an oxygen and two hydrogens, all covalently bound together, but then they're interacting through these intermolecular interactions. All right, intermolecular forces. In the grand scheme of things, these are not very strong. So unlike our ionic compounds, where we said those electrostatic forces were nice and strong, these intermolecular forces are not very strong. So then in terms of melting point, what do we think it would be for these compounds? High or low? Low. Again, held together by pretty weak intermolecular forces. All right, and because of that, these compounds are not very strong. Not very strong material. Often just called soft. All right, kind of easy to rearrange those that solid structure. Cool. All right, so ionic compounds and covalent compounds we spent a lot of time about, right? We divided the world into ionic and covalent compounds a long time ago when we were learning how to name stuff, and now we're talking about the different types of solids that they form, right? Ionic compounds, these strong compounds, whereas these molecular solids, they're kind of weak. They're held together by these weak intermolecular forces. They have low boiling points and are soft material. We're going to talk a little bit more about these intermolecular forces, but I'm going to finish introducing the different types of solids first. Okay? We got two more here. One thing that we haven't talked a lot about are just metals all by themselves, all right, or what we would call metallic solids. Ionic is a metal and a nonmetal. Covalents, all nonmetals. Metallic, as the name implies, are comprised of only metals. Okay, and that could be a pure piece of one of these metals, like a pure hunk of copper, or you can take metals and you can mash them together and form what are called alloys. They all have these same similar properties here. All right, and what we haven't talked about would be like the type of bonding here. So what do we see for our metallic bonding? This is what they call the sea of electrons model. Okay. If we look at our metal solid here, what we see are all these positively charged nuclei, right? So these are the very center of these atoms. Remember, the nuclei are in the center and they're positively charged. And on the outside, we have our electrons, right? So we got a bunch of electrons all over the place here. Okay? But importantly, metals, they don't really hold on to their electrons very tightly. Unlike the covalent compounds, unlike the nonmetals that have like a death grip on their electrons, never gonna let them go. The metals are like, meh, have at it, go well, right? So instead of these electrons staying fixed in this structure, they're kind of just all floating around, right? And so we say that our metallic solids are these positively charged nuclei, and they're just kind of floating around in a sea of electrons. Okay, so it's all just kind of this theory about metals not really holding on to their electrons very tightly. And so we have what we call the sea of electrons model here. The idea that our positively charged protons, our positively charged nuclei, are floating in a sea of electrons. one sort of consequence of this that we see all the time is one of the things that we like to make metals out are wires. And that's because electrons can move very easily through this solid structure here. So if I put an electron over here at one end, it has absolutely no time making it through that solid structure because all it's doing is then floating or swimming in that sea of electrons. Right? So metals are good conductors of electricity. I guess that's a consequence of this. All right, and I also just want to put down what we've discussed. Metals do not hold electrons tightly. That is a very important kind of concept to understand why these solids are so different. All right, this metallic bonding is also very strong. Metals are, for the most part, high melting point materials. All right. So in that sense, they're very similar to ionic compounds. Something that makes them very distinct to ionic compounds is how they react under force. All right, if we were to take our solid here and we're going to do the same thing, we're going to hit it really hard with a hammer in one part. And that's going to mess up this thing and everything's going to kind of get shifted here. Unlike my ionic compounds, where this then led to this like disastrous like charges repel one another type of thing, here, it doesn't really matter. It didn't mess up my network of bonding at all, because again, these electrons are free to just continue to float around, right? I haven't messed up my sea of electrons at all. So that's why metals don't break, they don't crack, they bend. Right? So if you take a hammer and you smack your car door, it's not going to crack your car in half. You're just going to put a big old dent in there. All right? So we consider that to be a malleable material. It bends under force. All right, so we have our metals now, metallic solids. This is now a new kind of bonding that we haven't discussed before that we call this sea of electron model. The idea that since metals don't hold on to their electrons very tightly, when they form this solid structure, they just have their positively charged nuclei that are floating around in a sea of electrons. Right? And that's also why metals are good conductors of electricity. Still a very strong type of interaction. Metals tend to have high high melting points. But unlike ionic compounds, they will bend under force as opposed to cracking. All right, and the last one is kind of a specialty boutique kind of solid here. Very, very rare, but nonetheless, we're going to discuss what are called network solids. If you remember how we were discussing molecular solids, and I made this whole big deal about how neighboring molecules were not covalently bound to one another. They had those weak intermolecular forces, right? A network solid is a solid where every atom is just covalently bound in one gigantic repeating network, okay? So in a network solid, all atoms are covalently bound. I actually think the real term is bonded, but whatever. Okay, so if we want to look, there are really just three that we're going to kind of highlight here. All right, I think the one that kind of illustrates this the best is a diamond. All right, a diamond is actually just a pure hunk of carbon. The only thing in a diamond are a bunch of carbon atoms. And what we do, if we look at like a chunk of diamond right here, what we see is we have, well, a carbon atom. I can't get off my selection tool, hold up. All right, we have a carbon atom. And it's got these covalent bonds to neighboring carbon atoms. And all of those carbon atoms have covalent bonds to neighboring carbon atoms. And all those carbon atoms have a bunch of covalent bonds to neighboring carbon atoms. And this just continues indefinitely. Every carbon in there has 4 neighbors that it's bound to. All right, so we just get this repeating array of these covalent bonds. So there's 3 substances that we're going to talk about. Again, the first one is a diamond, which is just a solid hunk of carbon. Carbon, you may have heard diamonds form under pressure, right? They're fairly rare in the sense that they're a hunk of carbon that's been subjected to a whole lot of pressure for a long period of time, and that's what kind of arranges it into that way. Another form in which we saw solid carbon, it's called graphite. So what carbon looks like when it's not under a whole bunch of pressure. All right, and then last one is a substance called quartz, which is silicon dioxide. Okay. Something that we see a lot of because sand, a good portion of sand is made up of this compound right here. All right, and if we were to zoom in, again, what we see is we have these silicon atoms. They're covalently bound to oxygen atoms, which are covalently bound to silicon atoms, covalently bound to oxygen atoms, et cetera, repeating in space. All right, so again, our network solids are all of our atoms are covalently bonded together. Okay, so because of that, these covalent bonds are ridiculously strong. So that means that our melting points are very high. All right, we're also going to call these, and it's kind of a lie for graphite at least, but these are considered to be very strong materials as well. Graphite kind of flakes pretty easily because if you see, it's really composed of these different layers, and it's not hard to separate the layers, but it is hard to break these bonds through the middle here. But if we think about diamonds or quartz, they are very strong material. Okay, cool. So first of all, let's just make sure that given some chemical formulas, you can place these solids into one of those 4 groups here. Right? We have these 4 different categories of solids: ionic solids, molecular solids, metallic solids, and network solids. Okay, so given the chemical formula, tell me what type of solid we're looking at. Potassium oxide. What do we got? Ionic. What about glucose? This is a molecular solid. Yes, it's a covalent compound that forms this molecular solid. Cu. Yes. It would just be a metallic solid if we had a hunk of copper. What about ice? Also molecular. Hopefully we beat that example to death here. All right, when we say table salt, first of all, the word salt hopefully gives it away because, again, that's just code for ionic compound in chemistry. But, of course, we know that table salt is really NaCl, our metal and our nonmetal. So absolutely, that's an ionic compound. And what about bronze? So that's a metallic compound. And this is a good example of an alloy. Bronze is not an element on our periodic table, right? It turns out that bronze is a mixture of copper and tin. You mix these two metals together, and it's stronger than copper is all by itself. Right? Wasn't there that period in history where they started making weapons out of copper and then quickly realized that if they put a little tin in there, they were that much stronger? Exactly. All right, yeah, metallic. Cool. All right, now I said that one of the things that I kind of mentioned with the molecular solids, kind of made a big deal out of it, are those intermolecular forces. We're going to talk a little bit more in depth about them, but we need to learn how to look at covalent molecules first, something that are called Lewis structures. All right, we're going to learn how to draw these from scratch. For right now, we just need to be able to look at them and interpret them. Okay, so whatever structure I put down, you're going to trust me that it exists. All right, but we need to know what we're looking at. Okay, so our Lewis structures, these are ways to represent covalent molecules. I guess that's a little redundant because when we say molecules, we mean covalent compounds, but whatever. All right, so let's take a look at an example here. We got oxygen. Oxygen is bound to 2 hydrogens. This is the structure for what molecule? Water, okay? And then our oxygen also has these 4 little dots on it. They always come in pairs. All right, now importantly, the sticks, these represent covalent bonds. And we say covalent bonds are what? What do we say about electrons in covalent bonds? That word, one word we should have synonymous in our mind. Sharing, right? So this represents a pair of electrons that are being shared. So importantly, each stick represents 2 electrons. But we also got these dots, and these dots live only on that oxygen atom. These dots also represent electrons, but they represent what we call lone pair electrons. These are non-bonding electrons. They're not being shared between 2 atoms. They're just a pair of electrons that lives on that oxygen atom. Cool. All right. We're going to talk a little bit more in-depthly about these structures, but now let's introduce our forces, and then we'll kind of go from there. And we're going to introduce these one at a time. We're going to start with what are the weakest intermolecular forces, weakest interactions that neighboring molecules can have with one another. All right. These are called dispersion forces. Or sometimes London dispersion forces. Pretty sure it's after a scientist, not the city. Okay? These dispersion forces are something that are present in all molecules. Okay? And that's because they are interactions that arise from temporary fluctuations in an atom or molecule's electron clouds. So this is going to be this key phrase, temporary fluctuations. In electron clouds. Or really, I mean, we should call them orbitals, but you will hear that phrase. Okay, so let's think about an ionic solid here. I'm not an ionic solid, that wouldn't make any sense. Let's think about a molecular solid here. Iodine, remember, if we look at our periodic table, it is a solid, right? Pure iodine is. But remember, it's also a diatomic compound. So that solid is a bunch of I2 molecules packed together. All right? So here is my Lewis structure for that I2 molecule. How many covalent bonds do we see? Just one, all right? And then we have 1, 2, 3 lone pairs on each of those iodine atoms in this structure here. All right, but if we're talking about a solid, we're talking about the interaction between neighboring iodine molecules. Okay? So each iodine, it's got these electrons, and they're sitting in this cloud here, these orbitals. So here's one on one, and here's one on the other. Okay? But in the chemistry world, in the atom world, nothing's ever just frozen still, right? So these things are constantly kind of moving around. They are these fluctuations that occur in these electron orbitals here. Same thing with this guy. His electron cloud is also bouncing around here. And every once in a while, there's such a time where the electron cloud of one gets to form this temporary interaction with the nucleus of its neighbor, right? The electron cloud that's negatively charged to one molecule is interacting favorably with the nucleus, the positively charged center of an atom and its neighbor. And this doesn't exist for very long at all because very quickly these things will bounce back. All right, so again, these are very temporary fluctuations in our electron orbitals. Okay. So a negatively charged electron can interact with the positively charged nuclei of its neighbor. But only for like a femtosecond, like a ridiculously short amount of time. Cool. So because of that, because it's just something that's quite rare and doesn't last forever, these are going to be really, really weak type of forces, right? We started out with our weakest of all of them, these dispersion forces. All right, now importantly, because all molecules have electrons and nuclei and all that stuff, all molecules have dispersion forces. Or dispersion interactions, let's say. Okay. But importantly, and because these are the weakest, if they have anything stronger, you don't really think about them, right? Because if there are a bunch of stronger interactions, these ones are going to be negligible. But importantly, there's a class of molecule that only has dispersion forces, what are called nonpolar molecules. Okay, all right, so now we got a new vocab term. Let's formalize this here. Where's my page? Nonpolar and polar. Very important concept in chemistry, kind of our first introduction to it here. By nonpolar, we mean that a molecule that has an equal distribution of electrons. All right, bipolar, we mean the exact opposite. A molecule where there's an unequal distribution of electrons. Okay, so then how can we tell if a molecule is polar or nonpolar? All right. Well, remember we had this is going to relate back to this other vocab word we introduced before, electronegativity. A molecule will be nonpolar if it contains bonds that are between atoms of similar electronegativity. All right, remember electronegativity, that tug of war over electrons in a bond. If two atoms have the same sort of tug of war abilities, none of them are able to pull electron density more than the other one. And so a very simple example, let's talk about a few examples. Would be I2, that first one that we laid out. Right? If we have a bond between two iodine atoms, it's not like one of them can be better than the other at this tug-of-war game. So there's going to be this nice equal distribution of electrons in that molecule. Another example, importantly, if we look at our periodic table, we all say that the tug-of-war champion is who? Fluorine. And the closer you are to fluorine, the more electronegative you are. And if you look, hydrogen's all the way on the other side of the periodic table, really far from fluorine. But given its position, it's actually a very electronegative element because it's still a nonmetal. It's kind of in the wrong place. We see this a lot with our periodic trends. And hydrogen's electronegativity is basically the exact same as carbon's. So if you have a bond between carbon and hydrogen, one of them isn't any better at tug-of-war than the other one. So any compound that has the formula CXHY is a nonpolar compound. Okay? Carbon and hydrogen have the same electronegativity, so they have an equal distribution of electrons when they form covalent bonds. And then polar is the exact opposite. This is a molecule that's composed of bonds between atoms of differing electronegativity. The bigger the difference, the more polar that bond is. Okay. Two more things that we're going to note about, what am I thinking? Oh, about dispersion forces. Okay. Importantly, bigger molecules, they have more of a chance for these temporary fluctuations because there's just more surface area. So we see that these dispersion forces, their strength will increase with the size of a molecule. And actually specifically surface area, just areas where neighbors can interact. All right, and the other thing that it increases with is just the number of electrons that an atom has. The bigger the element, the more electrons it has. So our strength also increases with the mass of an element. Very kind of simple way in which you can see this on the periodic table is by, again, looking at those halogens. Both chlorine, bromine, and iodine are all diatomic, right? But as we increase in the size of our halogen, it's only iodine that's a solid, right? So once we get that big, then those intermolecular, those dispersion forces are strong enough to keep it in the solid phase. Bromines aren't strong enough, which is why bromine's a liquid. And chlorines are even weaker, which is why chlorine is a gas. Okay, so they increase with the size or surface area of a molecule as well as with its mass. All right, that was the weakest one, the dispersion forces. Okay, those are, again, everything's got dispersion forces, but non-polar molecules only have those really weak dispersion forces. So if you're polar, you can do something else, what's called dipole-dipole interact. Okay. So let's take a look at a polar molecule. All right, I'm going to make a molecule that has a nice polar bond, like for example, a carbon-oxygen bond. This is actually a carbon-oxygen double bond here. You can see I drew two lines. So if one line is 2 electrons being shared, what does this double bond represent? 4 electrons being shared. Okay, now I'm only concerned about my polar bond here, which is not these ones here, right? We said carbon-oxygen about the same. So I'm focused in on this particular bond right here. And based on their position on the periodic table, I know which one of these is the more electronegative element. Oxygen. So that means oxygen's better at tug of war of this pair of electrons. It's pulling that electron density onto itself. So we would say that oxygen has a partial negative charge. And we use this fancy lowercase Greek letter delta. That's kind of like an S, but it's not. We kind of loop it back around. All right. And we differentiate. We use this to differentiate the fact that this isn't a full negative charge like we would have on an ion. It's just a partial negative charge. And since that oxygen stole that pair of electrons away from that carbon is left with a partial positive charge. So my oxygen's up here with all this electron density kind of glowing red hot, and my carbon's down here with not a lot of electron density. Okay, but we're talking about interaction. Oh, and this right here, this separation of charges that we see in a polar molecule, we call this a dipole. Molecule's got one end that's positive and the other end that's negative. That's what we call a dipole in our molecule. All right, but when I'm not just talking about a single atom here, I'm talking about the interaction between neighboring molecules, right? So now I'm going to draw in a second one of these molecules here. This second molecule also has this dipole, where one half of that molecule, that oxygen, has that partial negative charge. And the other half of that molecule, that carbon, has a partial positive charge. Okay? And so this dipole-dipole interaction is the negative end of one molecule interacting favorably with the positive end of its neighbor, right? The partial positive oxygen of one molecule interacting with that partial negative oxygen of one molecule interacting with the partial positive carbon on its neighbor. Okay, so our dipole-dipole interaction, again, the partial negative end of one molecule interacting with the partial positive end of its neighbor. All right, so by definition, polar molecules have this unequal distribution of electrons, and that leads to this interaction between neighboring molecules that's that much stronger than dispersion forces, what we call dipole-dipole interactions. All right, one more to go here. What are called hydrogen bonding interactions. Hydrogen bonding. Okay, this is actually just a dipole-dipole interaction, but between one of three very specific bonds. Okay, so this is a dipole-dipole interaction. Between molecules that have, and what we're going to see is they're all of our teeny tiny, very electronegative elements, a fluorine hydrogen bond, an oxygen hydrogen bond, or a nitrogen hydrogen bond. All right, so I'm saying it's just another dipole-dipole interaction. What I mean, so let's just draw a compound that illustrates hydrogen bonding here. A great, easy example is water, because water has those oxygen-hydrogen bonds. All right, if I look at this molecule and I put in those partial charges, where should I put my partial negative charge? On the oxygen, because that's the more electronegative element. And what about my partial positive charge? On those hydrogens. So then if I got two water molecules next to one another, I see that that partial negative end of one is able to form a nice interaction with the partial positive end of its neighbor. Right? We colored these in red and these in blue, but these are exactly what we saw previously as well. All right? But we're going to put them in a separate category that we call hydrogen bonding because they're just that much stronger than other types of dipole-dipole interactions by kind of a lot, right? Enough that we're going to give them their own separate category. Because again, we ranked these different intermolecular interactions from the weakest to the dispersion forces. The middle were dipole-dipole. So our strongest type of interaction is that hydrogen bonding. All right, cool. So I'm going to put down some Lewis structures, and I want you to tell me what is the strongest intermolecular force that these molecules will have with their neighbors. The strongest intermolecular forces that you see here. Okay, again, you don't really know how I got these structures. You're just going to trust me. All right, we're worried about reading them at this point. Okay, for this first one here, what are the strongest type of intermolecular interactions that it would have with a neighboring molecule? It's got hydrogen bonding. We got these polar bonds. All right, but not only are they polar, they're one of our special three on our list here. They're nitrogen-hydrogen bonds. So these are capable of hydrogen bonding with neighboring molecules. To be clear, everything up here has dispersion forces, right? But the strongest one, the one that we're going to pay attention to the most in terms of the behavior of these molecules, are these hydrogen bonding interactions. What about this one right here? Yeah, this one's only dispersion forces, right? Because the only thing in here are carbons and hydrogens, and none of those bonds are polar. Okay, and then this last molecule here, what do we think? Dipole, dipole, right? We got these polar bonds, these carbon-oxygen bonds that are polar, but we don't have any oxygen-hydrogen bond, so this can only dipole-dipole interact. All right, remember we put these on this like listing of like weakest to strongest here. So I want you to try to predict which one of these would have the highest melting point and which one would have the lowest melting point. What do we say about ionic compounds? Why do they have such high melting points? Because they have those strong interactions, right? So now let's look at these solids here. And again, try to tell me which one's going to have the highest melting point, which one's going to have the lowest melting point. When I melt something, I have to break intermolecular interactions. How much of that heat do I have to put in to break those interactions? Well, if they're those super weak dispersion forces, I'm not going to have to put much energy in at all. This compound here would have the lowest melting point. And the one that forms the strongest interactions with its neighbor is going to have the highest melting point. Now, truthfully, all three of these are pretty small, so they're pretty low melting points here, right? But if nonetheless, we can definitely say this molecule right here is going to have the lowest melting point because it has those weak dispersion forces. This molecule is going to be somewhere in the middle because it's got those dipole-dipole interactions that are a little bit stronger. And this one's going to have the highest melting point because it has the strongest intermolecular interactions. Cool. All right. We're going to kind of just take a second to introduce, and then we'll pick up with this next time. Our topic for what we're going to discuss starting next time is what's called calorimetry. All right, this is the study of thermal energy exchange. In a chemical reaction or phase change. All right, remember we were talking about melting and boiling and all that jazz, right? So this is going to be kind of a natural, and again, our focus for this particular chapter is solids as well as liquids, right? So we've already talked about how we put heat in order to melt something. We haven't kind of really introduced what that even means by heat, okay? So thermal energy is a fancy way of saying heat. All right, and importantly, heat is not the exact same thing as temperature. All right, they're closely related, but they are not the same thing. And importantly, they're measured in completely different units. What do we measure temperature in the lab? Celsius. And what do we measure heat in if it's an energy? Yeah, we have these units for energy, either calories or joules. Joules is kind of the favorite of scientists. It's actually kind of messed up because the biochemists love calories and the other chemists like joules. The physicists like joules, right? So we're kind of in the middle. Okay, so they're measured in these different quantities here, all right? So they're very closely related. If you add heat to something, you will raise its temperature. If you take heat away from something, you will lower its temperature. So I'm not saying there's no relationship, but they're just not the exact same thing. Okay? And what we're going to do first is study this relationship Q equals HC times M times delta T, our calorimetry relationship here. All right, in this equation, the Q is our heat, is our thermal energy. And we can see on the other side, it's equal to a bunch of crap times delta T, right? What do we think the delta T is? Change in temperature. So again, there's this relationship between heat and temperature. They're just not the same thing. And this equation here helps explain that relationship. Okay. The amount of heat that you have to put in to change something's temperature depends on how much of it you have, right? And we all know this. If you're going to make a spaghetti or something, the little pot of water takes less time to boil than the big pot of water, right? You got to put more energy in if there's more of it, and that's what this term M is. The amount of energy that we have to put in order to change something's temperature is going to depend on how much of it we have, the mass of that substance. All right, and then the fancy term here is this HC. This is what's called the specific heat capacity, or specific heat or heat capacity. All right, and so what we're going to see added on to our constants page for this chapter is a table of different specific heats here. We have these different substances, aluminum, gold, graphite, and copper. And then we have these numbers next to it, which are those constants, those specific heat capacities. Let's look at the units real quick. Joules over gram degree Celsius here. All right, so the way that we think about these specific heat capacities, it is simply the amount of heat, the amount of thermal energy required to raise 1 gram of a substance by 1 degree Celsius. All right, so this specific heat, these values that are listed here, it's the amount of energy you got to put in to raise 1 gram of that substance by 1 degree Celsius. We can see that it's different depending on what substance we're talking about. All right, which one on our table here is the most difficult to heat up? Which one do I have to put the most energy into? Water. Water has our highest value of 4.184. You see that all of our metals are like sub 1, right? And again, this is something that we have some experience with in the kitchen. If you take a pot of water and you put it on the stove, it doesn't take very long at all for the pot itself to heat up, for that hunk of metal to heat up, and then you gotta wait and wait and wait for your water to heat up, all right? That's because water has a higher specific heat. You have to put in more thermal energy in order to heat that 1 gram of water by 1 degree Celsius than you do that big hunk of metal. Cool. All right, we'll pick up with that next time. Break.